Hey stat students, so today we're going to learn about chi-squared tests. You learned about chi-squared goodness of fit tests last class, but now we're talking about a different type of chi-squared test. All right, so some characteristics about chi-squared tests are that they're commonly used for testing relationships between categorical variables. Okay. And for these chi-squared tests, so there's chi-squared goodness of fit tests, there's chi-squared tests for homogeneity, and chi-squared tests for independence. Chi-squared tests for homogeneity and independence, which is what we're learning today, can be just referred to as chi-squared tests. Chi-squared goodness of fit tests are always referred to as goodness of fit tests. So if we just say regular old chi-squared, we're assuming we're talking about one of these two tests. Okay, and so chi-squared tests are usually represented in two-way tables. Okay, so the data is represented in a two-way table. Because for chi-squared tests, the data isn't necessarily univariate. We may have multiple variables that we're looking at. And one thing to remember that we kind of touched on is that a large chi-squared statistic indicates a small p-value, which indicates that there may be a significant difference between whatever we observed and what we expected. Okay, so the larger the chi-squared value is, the further away from 1, we are expecting that we're moving away from the null and towards the alternate hypothesis. Okay, tests for chi-squared tests for homogeneity. All right, so we're going to label this one with red throughout this document. Okay. This is a test to decide if the category proportions are homogeneous, meaning the same across the populations. And those categories and populations are usually in context. Okay, and a test for independence is a test. Enough. Is a test to decide if whatever categories we have and the populations are independent or not associated. The two phrases can be used interchangeably. If two things are independent, they are not associated. Okay, so we're going to do a 9-step test now. The 9-step test is exactly the same for homogeneity and independence. The only part where things get different is defining the null and the alternate. So for these notes, I will write the null hypothesis for homogeneity over here, the null and the alternate. And I will write the null and the alternate for independence over here. So the rest of the test is exactly the same. The way that you fill everything out, it's just when you get to step 2 or 3, you'll decide, are you doing homogeneity or are you doing independence? And then you'll proceed like normal, okay? All right, so the first step is that you want to define your populations and categories. And by define, we mean list them out. So we've got populations and categories. Normally, populations have to do with, people or subjects, and categories are decisions or choices that are made by those people or subjects. But if it's really hard to decipher between the two, when in doubt, you can always just kind of follow the definition. If the categories are homogeneous across the populations, and for independence, you can kind of just use your best judgment. It is not going to kill your chi-squared value too much. Okay, so for chi-squared tests of homogeneity, the null is that the categories, and this should always obviously be in context, are homogeneous or the same across the populations. And really what just matters the most is that whatever you define these as up here, you carry through the rest of your test. Your alternate, is that these categories are not homogeneous or the same across the populations. Okay, and our chi-squared test for independence, the null is categories are independent of the population. Remember, independent also means not associated. So you can write it that way if you would like. And the alternate is that the categories are not independent. Or they are associated. Of the population. These will be the same every single time, okay? So these are always the same. OMG. Okay, so they're always in this format. You just need to decide whether you're carrying out a test for homogeneity or a test for independence. Otherwise, every other step, 1, 4, 5, 6, 7, 8, and 9 are exactly the same regardless of the test. All right, let's go down here and talk about finding expected values and checking conditions. Okay. So you do have two conditions. They are the same as goodness of fit tests. The first one is that the data is random. And the second one is that the expected cell count is greater than or equal to 5. However, now we're dealing with a two-way table, so calculating expected cell count looks a little bit different. What the expected cell count is now, how we calculate it, is the row total times the column total over the total over everybody, okay? That's how we calculate each expected cell count. And those need to be greater than or equal to 5, okay, to proceed without caution. All right, state the formula and the test. So each time you are definitely going to say that this is a chi-squared test of whichever one you choose, homogeneity or independence, depending on the context. And the formula is the same, luckily, because the statistic is still the same. Just how we calculate it is a little bit different. All right, you're going to evaluate this formula using your calculator. So you are going to get that chi-squared equals some value on your calculator. So here's those calculator pathways for you. All right, so we're doing stat tests, chi-squared test. The only difference is that we aren't using lists. We aren't able to use lists for chi-squared tests because we aren't using a frequency table. We're using a two-way table. So in order to use a two-way table, you have to use matrices. So within this, you're going to have a matrix A for your observed data and a matrix B for your expected data. And how you fill out these matrices is you hit second matrix and we input this information into matrix A and matrix B. Last thing that you need to know about this is that your degrees of freedom are equal to the number of rows minus 1 times the number of columns minus 1. So that's helpful and easy. All right, step 8 is just like any other. You're going to write your probability statement. Chi-squared is always greater than whatever statistical value you get from step 7. And same thing as usual, if it's greater than alpha, then we fail to reject the null. And if it's less than or equal to alpha, we reject the null. And of course, you need an in-context conclusion. All right, let's move along with these examples. So here we go. The report, undergraduate students and credit cards in 2004, classified students according to region of residence and whether or not they had a credit card balance of more than $7,000. Is credit card debt the same in every region? Use a significance level of 0.05. All right, so the first thing that we want to do is we want to define our populations and regions, or populations and categories. So in this case, we're looking at, is credit card debt the same in every region? Are the categories the same across the populations? So regions are populations. So these are regions. And this is whether you have a balance over $700 or not, with the option of yes or no. And up here we have the option of Northeast, Midwest, South, and West. We know this is a test of homogeneity because it says right here, the same, okay? So that is an indicator that we have a test of homogeneity here. So my null is that credit card balance is the same across the regions. And my alternate is that it is not the same. All right, step 4, check conditions. Condition A is the sample random? And it doesn't say, but it has no indication that it's clearly voluntary or anything like that. So we'll assume. And is the expected cell count greater than or equal to 5? All right, so here we go. We're gonna come up here and we're gonna total out all of these rows. So this row, sorry, I'm running out of room right here. This column totals to 241. This column totals to 1,318. Now let's get the row totals. This row is 565, 344, 523, and 127 for a total of 1,559. So expected cell counts, I'm gonna just come in here and leave a category for expected cell counts. So observed cell counts are typed. Expected cell counts are going to be in blue. So remember, expected cell count is the row total over column total divided by total. So right now I would take a minute, pause this video, and fill in this table. So row total times column total over total for here. Row total, column over total for here. For this one, for instance, row total times column total over the total. So I'm going to pause it and you guys fill this in. All right, so check your expected cell counts. Now we're going to move on to step 5. Alpha is equal to 0.05. And I'm actually going to squeeze step 6 in here. This is chi-squared test of homogeneity. And here's my statistic. Okay, so since we're not in person, you're gonna have to listen to my voice very carefully, and you may have to rewind and do this a couple of times, okay? So what we're gonna do now is we are gonna hit second matrix on our calculator. Matrix is above x to the negative first. And we're gonna tab over to the edit button and hit enter for matrix A. For matrix A, we have a 3x2 matrix, okay? Or I'm sorry, my apologies. A 4x2 matrix, I can't count, okay? So we say the number of rows and then the column. So we've got a 4x2 matrix. And you should see in front of you something very similar to what you have going on for the expected values. So expected values or observed values go into matrix A, expected values go into matrix B. So observed values, you're going to enter in your matrix 28, then 537, then 162, 182, then 42, then 481, then 9, then 118. When you're done with that, hit second matrix again, tab over to edit again, tab down to matrix B, hit enter. We still have a 4x2 matrix. These will always match. And now you're gonna enter your expected values. 87.341 in the first, 477.66. This is how they get entered, okay? Until you have all of them done. All right, then you're gonna hit stat, tab over to tests, and you're gonna go down to option C, which is a chi-squared test. It should already have auto-filled there for you, observed values in list A and expected in list B, which is what we just did. If you need more time, pause the video, rewind, listen to my voice, and follow the instructions over and over again until you've got it. When you hit calculate, it will give you your chi-squared value, and for this one, it is 339.99. Yikes, that's pretty large. And so the probability of chi-squared being greater than 339.99 is equal to approximately 0, which is less than or equal to alpha, so we're rejecting the null here. So for step 9, with a p-value of approximately 0, the data strongly suggests different regions have different credit card balances. Okay. In a certain town, there are about 1 million eligible voters. A simple random sample of 10,000 eligible voters was chosen to study the relationship between age and participation in the last election. We want to check whether age is independent of having voted in the last election. This keyword right here lets us know that we are doing a chi-squared test of independence, and the context will always let us know, okay? So here we go. First one. Let's go ahead and define these populations and categories. Usually your population has to do with people, and the category is like a choice that the people are making. If it's really hard to tell, it's okay if you switch them. So for us, I would choose the population to be age. So we've got under 30 or 30 and over. And categories, we have participation. And I could have chosen yes or no. All right. Step 2 and 3 always are going to be very similar to this. So participation in the election is independent of age. Or participation in the election is not independent of age. All right. Step 4, check those conditions. A, is it random? Stated. Yay. B, are those expected cell counts greater than or equal to 5? All right, let's go up here and total everything out. Right here, this is a total of, again, I didn't leave enough room, but sorry, it's 3,617. And this is a total of 6,383. We've got a row total of 5,722 and 4,278 for a total of 10,000 people. All right, I'm going to make a little separation for my expected cell counts. And remember, your expected cell counts are row total over column total divided by total. I'm going to pause the video. Go ahead and calculate those now and see if you get them right. Okay, guys, there we go. Step 5, alpha is equal to 0.1 here. Step 6, this is a chi-squared test of independence. Here's our formula. And step 7, we're going to calculate that chi-squared value. So you are going to hit second matrix on your calculator. Tab over to edit. We have a 2 by 2 matrix here. In matrix A, you're going to enter the observed values. When you're done, you're going to hit second matrix again. Tab over to edit. We'll edit matrix B, which is also a 2 by 2 matrix. And then you will enter your expected values in this way. After that, you will hit stat test, tab over to chi-squared test, and the observed are already in matrix A, expected already in matrix B. Hit calculate, and you should get a chi-squared value of, OMG, 6.660. All right, probability statement, chi-squared being greater than 6.660 is approximately 0.009, which is less than 0.10, so we're rejecting the null. So with a p-value of 0.9%, the data suggests we reject the null and that age is not independent or age is associated with of participation in the election. All right, you guys, so go ahead and take this time to go back, rewatch, pause if you need to, write down any questions you might have for me. Try these 2 examples very quickly so that when we come back in class on Friday, we can go over them. Okay, so chi-squared tests of homogeneity and independence, very similar. And that is all we're learning this unit is all about chi-squared tests. So we have finished the unit, the little mini unit. So review on Friday and we'll have a quest on Tuesday. So you guys try it and we'll go over on Friday together.